and that sort of thing. Okay, so we got through F ratios. So we want a really large F ratio where the good variance, the differences between means, is large, and the bad variance, the errors, are small. Okay. And now we're getting into the unfortunate part, which is all the math. Okay. So these are all the formulas. One of the formulas in the book is not wrong, it's just incomplete. And so I've corrected it here and in your notes. But in the book formula, they don't have N here. And that's incorrect. So we're going to go through these one at a time by using the source table. So what I tell you to have open while we do this is the example doc. And it's got the source table on here. And so this is what we're going to do. And then do it by hand. And see, it has the little, I put the corrected piece on here. Okay. So what is a source table? The source table makes the calculations in a easy to read format. We'll use this term in quotes. This first time you see it, you're like, what's going on? But it helps lay out what's going on in Anova. So what we've been doing is variance. Remember, this is analysis of variance. So we've been doing variance like this. Okay. So we talked about how this is called sum of squares very briefly once. Okay. Because this is the sum of the squared deviations from the mean. And then this is degrees of freedom. So that's not important now, we'll come back to it. So now we're going to come back to it. And what the source table does is it breaks apart sum of squares and degrees of freedom into two different pieces. So it breaks sum of squares into two parts, degrees of freedom into two parts, because we've got groups and people. Before we always had the same number of groups, so we didn't have to deal with that. We just dealt with people. Now we have to deal with how many groups, how many people. So we have 2 degrees of freedom. And so it creates the variance like this is variance. So sum of squares over degrees of freedom, which we're going to call mean squared. And so we'll walk through what are these things and how do they work here one at a time. So when I ask you to include the source table, this is what we're talking about. These are the actual formulas instead of the labels. Anyway, let's work one. So we're going to try to calculate the first column, sum of squares within, between, and total. So you're going to need that chapter 12 data.
Is that the, oh, that's CSV, sorry.
Yeah, the CSV online. So I'm going to load that up by import dataset from text file, chapter 12. Give you guys a second to load that. So we should end up with a data set that's got our 3 different groups. So you have to remember these are different people in each one. So we actually have 30 people, 10 in each group. It's not repeated. Each person only got one type of snack. I'm going to start with sum of squares total. And what sum of squares total does is it finds the total variance in the experiment. It's kind of like how much variance do we have to work with? So overall variance, and this variance is partially due to the independent variable, what we changed between groups, partially due to error, because there's always a little bit of error. So if I have the total, I know how much to divvy out. So this is like counting up how much you have before you give it to people. So we're going to start with sum of squares total. That's going to break down into sum of squares between. I can't spell. Sum of squares within. Okay. So this is due to the IV and this is error. So this is overall variance. How much variance do I have that I can break down into parts? We're going to calculate this by hand just for demo purposes. When you get to running this on your own, you will always just run the easy Anova code at the end. So right now it's just to show you like how it's being calculated. So it should let me copy this. Listen, I already had a grumpy dog this morning. I don't need grumpy R as well. There we go. So I imported minus chapter 12. And I'm going to take the grand mean. So I'm going to take each person minus the grand mean. Okay, why the grand mean? Well, we talked about we have cheese. Well, this is candy. Fruit. And then cheese is kind of close. And I'm going to calculate the grand mean. And I'm just figuring out how far apart everybody is. So what that really does for me is it creates a new distribution where everybody's in the same group. And we just pretend like everybody's in one giant group. This is the null hypothesis idea. There's no differences, so we treat them all as the same group. And I'm going to calculate how far they are away from the middle of the middle. So it's each person minus the grand mean. So this is total variance. So that first line of code, this unlist thing, just calculates the mean of all of the columns. So unlist just treats it as one giant data set instead of 3 columns and gives me the mean. So it's 4.7. Now I want to take each person, subtract the mean, square it, and add it up. So that's all I did. So I did each person in chapter 12 data set, so all 30 people, minus the grand mean, 4.7, squared, remember the little caret thing means squared, add it up. Should give us 96.3. I'll mark her right. So I have 96 points to work with. Hopefully most of that is due to the IV and not the error. Because remember, you always want your IV variance to be bigger than the error. Okay. So calculate total variance. Now we're going to do error variance. Okay, so I'm working my way from the bottom of the source table up. So it's each person minus their own group squared. And so that's the old variance equation, x minus the mean squared. And the logic of this step is that we don't know why people differ within their own groups here. So why doesn't everybody rate candy the same, fruit the same, and cheese the same? And that's individual differences, is what a lot of people call it, but that's error. So I can probably guess why the means are different between each other, because they had different things to rate. But within each mean, I don't know. So I am calculating that as error. So how different are you from your own little group? And that is SS within. Okay, order. So we kind of do that one piece at a time, because each group has a different mean. What I did here, so this is sum of squares total. This is SS within. Everybody's favorite function, summary. The summary told me what the means were. I got 6.3 for cheese, 2.7 for candy, 5.10 for fruit. So cheese and fruit are kind of close together, candy's further on the end. And then I use that same function. So I got cheese minus its mean, so only the cheese column. Only the candy column minus their mean, only the fruit column minus their mean. Instead of everybody minus the grand mean. So we went from how different is everybody from the middle to how different are they within their group. So you should get 8.1, 8.1 because it's made up data, 12.9. And then you add all that up, and that's 29.1. So 29 of these 96 points is because people vary within their own group. So I've carved out a piece of that, and I said, well, part of this is just error. I don't know why this is. So we should get that the other 60 points is due to the IV. So we're kind of breaking this down by where the variance is. So we got overall variance, and then where is that variance happening? Well, this is all error. So between is kind of the more important one. Let me make this bigger. Some squares between here is each group minus the grand mean. Squared times n. The book doesn't include the times n thing because they're just talking about like the logic of it, and then it's like if you tried to do this by hand, you would totally be confused because the total wouldn't add up. So I'm taking each person minus the grand mean. Right, we did that one. We did each person minus their own little group. Now I'm doing overall group minus the grand mean. So how different is candy from the grand mean, fruit, and then cheese? So we're sort of assuming the grand mean is the null, that everybody is actually probably this middle score and they vary just by chance. And so we've got, the reason this breaks down, and it works where you can split it up, is that I've taken everybody minus the grand mean, and I've taken this little piece and then this spread. So we've been able to attribute it to error or IV. Now why is it times n? That seems kind of like, oh yeah, by the way, throw this n in here. Every one of these formulas includes x. Okay? So this is each person minus the grand mean. So that's got 30 people in it. This is 30 people minus their own group. And in theory, this only has 3 numbers in it. Right? Each mean minus the grand mean. But every person's got to count, so this is kind of the Oprah of this section. So it's each mean minus the grand mean, but there are 10 people here. So it's got to count 10 times, 1 for each person. And the overall logic of this section is to measure how much of the variance is due to group differences, not individual differences. So we've got the total, which is group and individual, or error and IV. We figured out the error, how different are they from their own little group, and this is how different are they from the overall groups. And so I did that one by hand because it was easier. Right. So each group mean from summary minus the grand mean squared times the number of people in each group. You can use R to write big long formulas, but this to me made it more obvious what I was doing. And so if I just plug that in, I don't know why it's copying so nicely today, but I'm going to take it. Right. That's where I got 67.2. Do these two things add up? Yes. Because it didn't when I did it the first time, because I forgot that I had left out n. All right, so on your little sheet here, these go here. So we've got 67.2, and then our error variance is 29.1, and then our total is 96.3. I kind of did them in the reverse order because it's easier for me to explain that way. But the big thing to get is going to call it between groups and within groups, but I always think about this as what does it do to my IV, what I want to have happen. This is the part that I'm concerned with versus what is error. People are varying because they're weird. Let me save this real quick so I can upload it. And then I also included it in here just to be clear what we were doing. All right, so that's probably the hardest part. The next section is about degrees of freedom. So we've been doing degrees of freedom as n minus 1, like all semester, n minus 1, n minus 1, n minus 1, n minus 1. It's still n minus 1. On the next test, it's not. I'm sorry. But for single sample t, it's n minus 1. For paired t, it's n minus 1. For independent t, since I have two groups, it's n minus 1 minus n minus 1. Oh, plus, sorry. So you can probably guess it's still going to be n minus 1. But it depends on what the formula includes. So for sum of squares between our IV, it's mean minus grand mean. And there are only three means. So it's groups minus 1. So since I'm using the means instead of people, okay, so the mean here, it's groups minus 1. Okay, so it makes it 2. Degrees of freedom within, I'm still using people, so it's n minus 1 plus n minus 1 plus n minus 1, repeat. For our example here, it's 2, groups minus 1, so 3 minus 1. 27, so 10 minus 1 plus 10 minus 1 plus 10 minus 1. And then the total is n minus 1, 29. And that just depends on what they're doing in each one. So since it's x minus the grand mean, it's the number of x's minus 1 grand mean. Since it's x minus m, it's the number of x's minus the number of means. So 30 minus 3. Since it's mean minus grand mean, it's the number of means minus 1 grand mean. Okay, so it matches the formula. Okay. I don't know that I had that epiphany until like mid-grad school, so if you don't get it, just check my word for it on the formulas. Okay. It's a variation on n minus 1. So for here, we've got, and I'll write it out, 3 minus 1 is 2. Don't know why it's, so 10 minus 1 plus 10. Ooh, that looks crazy. It's 27. And then this one is 30 minus 1, which is 29. And they still add up going down. So the cool thing about the source table is it adds going down. And as you'll see when we get to mean square here in a second, it divides going across. So one thing I want you to do real quick, is put like x's or something here, here, and here. Whatever word, you can capitalize if you want. Okay. So there won't be any numbers in those squares. They'll be blank. And so literally all I have for this one is divide, but let me back up and show you the formula. Whoop, whoop. Here. Okay. So for mean square, so what does mean square mean? It's called mean squared error. So sometimes in reports you'll see people write MSE. For some reason we've dropped the E, but it's mean squared, which in a sense is like S. Okay, we've been talking about standard error all semester, and the symbol was SM. I think they're just like, well, we can't use that again. Let's just switch them. So it's mean squared error because it's not standard deviation. Right? We never take the square root through this entire chapter. So it's just called mean square. And that is variance. So I'm going to take sum of squares divided by degrees of freedom. So essentially, this column is the variance column. So I'm taking this one divided by this one. Is mean square between. You want this number to be really big. Okay, hopefully. And then I'm going to take sum of squares within divided by sum of squares degrees of freedom within, and you want that to be small. So let me look at the one that we have here. Okay. So I'm just dividing the going across. 67.2 divided by 2 is 33. So that's 67 is based on degrees of freedom of 2, or 3 groups, if you will. And so I still have to divide to make this variance. So I'm taking out the fact that there are 3 groups, and there might be 5 groups, and then it would be, degrees of freedom would be 4. Now for within groups here, that's a lot of people. So we're dividing by the number of people, okay, or the degrees of freedom for people, so we got 1.08. And then here we don't really do anything. The total column is really to make sure that you have the math on the first 2 columns right, and then we divide going across. So we took the amount of variance that was due to our IV, and then we said, well, we've got several groups, so we're going to divide that up by groups. So 33 points for variance is do the IV, controlling for group. We said there's 29 points for variance, but that's a lot of people, so we divide by the people. So each person's about 8. Or, sorry, that's not an 8. That's a dyslexia. That's a 1 for each person. Why don't we divide by the number of people and the number of groups? That goes back to the when we talked about standard deviation the very first time. Okay. So why is it n minus 1 on the bottom? We have to assume a little bit of error. So I've divided. Wait, we're going to divide once more. Okay. And so F, the ratio, is the ratio of between groups variance to within groups variance, so we divide these two. So the first time you divide this way, and then you divide down. Okay. Why did I stick F here? I don't know. So remember from the very beginning where we were talking about like Y Anova, talked about F being the variance between groups to the variance within groups, and all of the first couple of columns are just getting those numbers. So I always think about this as a ratio of good variance to bad variance. We want our good variance due to our IV to be much higher than the variance due to the error. At 31 points is a good number. F can get really large. I've seen 6,000. So one of the issues with F is it can be very, very big. So that's how we create the source table. So I didn't finish here. Why are you in? Stop. I love how word is like, I'm going to do whatever I want sometimes. So what do I do with this F number? I have it. What does it mean? And this is where we'll get into doing the 6 steps. I'm not entirely sure we have enough time to get through all of one of them. But I do want to kind of describe what does F mean before we get into working an example. So we talked about this being the ratio of good variance to bad variance. So here's F. Remember, it's t squared, so it's folded in half, so it's all positive. And it's all positive because look at all these formulas. Squared, 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 and then we're just dividing. So it's never negative because it's always squared. Hence the analysis of variance. Remember, variance is always squared. And it makes things a lot easier too. We found a 31 as our ratio of variance. Most F values are 1 or less. So that's 1, or just go all the way to 0. Okay, because it can't get negative. And because an F of 1, remember it's between variance over within. What does that mean if F is 1? That means the ratio of your between subjects variance is the same to your within subjects variance. Right? It reduces down to 1. That means all of the variance due to your IV and the variance to your error are the same thing. Okay? A ratio of 1 to 1 might be good in gambling, but it's not good for Anovas. Okay? So that means that all the variance, it might be because of your independent variable, your manipulation of groups, it might be error, you have no idea. So to make bad Hunger Games jokes, you want the odds to be in your favor? Yeah. I feel like I used to say that all the time, and now I feel really cheesy saying it, but it's an odds ratio. I want the odds of my relationship, my IV to be much higher than my error. So this is just the odds of it being more IV than error, okay, or more between to within. 1 second. And so we want this number to get really big. Okay. So it's a ratio of good variance to bad variance. Yeah.
So this might be a discussion, not a discussion to have, but does that also assume the fact that chance is blind but we're not? So when you say 50-50, you tried to make something happen, and it's not like chance tries to make something happen. So,
ooh, yeah.
I mean, if you get a 1-to-1 and you were actually trying to make something happen, does that take into account the fact that you were...
So you were trying to make it happen?
Yeah.
That's good research design, controlling for experimenter bias.
Okay.
So, like if you all take an intro, that clever Hans story about how they get the horse to tap his foot or whatever, and that's like the experimenter leaning in. They're doing those unintentional things. So running this study without letting people know that there are different groups, and then without the experimenter knowing which group the person's in.
Okay.
So those are called double blind,
Okay.
where they don't know which. I mean, they know what group they're in. They're in the cheese group, but they don't know there are other groups. But the experimenter doesn't know when they're handing it out, so you can't influence it.
Okay, so from like a statistical perspective, when you do a double blind, you're trying to make yourself resemble chance as much as you can.
Yeah, I mean that's on the research end. The number wise and no, not really. It assumes that the numbers are what they are.
There.
Yeah. I guess there are ways to control for that, but that's like 3 classes later.
Okay.
Yeah. So, Anova. So what we'll get to, probably not today, but in one of the videos / Monday, is how do I know what's big enough? So we'll use the PF and QF. So the R code doesn't change too much. We're going to have 2 degrees of freedom, okay, because we have to deal with both groups and error. So just want to get into like, what does F mean? Because sometimes in the questions online, it'll ask you, like, what is F? So it's a ratio between subject experience to within subject experience. Okay? Informally, you could think of that as an odds of my study working to not. Okay, so let's do a little bit of this thing. We won't make it all the way through it, but it'll be okay. So, the assumptions for Anova are the same 4 that we did for independent T, except in the book they like lose their minds and they call this homoskedasticity. You can call it homogeneity, but if you see this giant spelling word pop up in the notes, they're talking about homogeneity. When we get to regression, we'll talk about how are those 2 things different. In Anova, they're not. They're basically the same idea. In regression, they're very different questions. So I wish they wouldn't do this in the book, but they do. And so the idea is that each group has the same variance. So this is called equal variances or homogeneity, which we did with independent T. So for this specific example, okay, is the DV scale. Yeah, it's interval. So we're rating things from 1 to 10, so there's no 0, but it's an interval. And then, is it normal? Oh my god, we have 30 people. Yay, 30 people. That's the first. I know we've been picking on the book for the questions always being 15 people. Right, and this one, Anova, is pretty popular for it to be 10 in each group. Random selection. Yeah, no, probably not. Right, if I look at the question, it doesn't even say, oh, they're at a lunch, so they're very convenient. That was one of the most missed things on the test, by the way. It's convenience sample. So that's a no. But random assignment we could do. So I can randomly assign which snack they get. This is like half modeled after a study I feel like the eating disorders lab did a million years ago, where they had people like watch something and then they had snacks out and they were seeing which one that people picked. So if they watched something about eating healthy, they were more likely to pick a healthy snack. Then if they just watched something neutral, they would more likely to pick Coke or candy.
So even though the researchers didn't randomly assign, it's just that it's possible that they could do this if you decided to rerun this experiment?
Yes. It doesn't say if they did, but we certainly could. Right. Yeah. We're kind of assuming that they did. They didn't just hand out the first 10 to the first 10 people there. Right? But yes, you're correct. And then the newest one, homogeneity. And I'll have to look at the variances. We've actually kind of calculated them already, but normally you're not going to do that table by hand. That was just to kind of try to explain like where all these numbers coming from. Okay. So at this, if we're pretending that we just started, we don't have these numbers. Now, step 2, so we're going to label each group and only use, not us, use, equal to and not equal to. So we're always doing a 2-tail test, and you go, but you just told me it was 1 tail because we folded the whole thing over. So technically it's a 1-tail test, but because we've taken both tails and folded them in half, we're going to use 2 tails because both tails are at the same end. So we're going to do equal to and not equal to, and then when we get into post hoc tests, we'll talk about why. All right, so we're just going to label all of our groups. So we've got cheese, candy, fruit. And then cheese, candy, fruit. So for the research, they're not equal. So that actually makes this chapter a little easier. There's no 1-tailed, 2-tailed thing to work on. It's always 2 in a sense. And then that one. So the hypothesis is that all of them are not equal versus all of them are equal. But that's not really how ANOVA works. Really what we're saying when we do ANOVA is something is different versus, I don't know why exclamation point, but something is different versus nothing is different. But this is the formal way to write. So in ANOVA, the question isn't that they're all different, it's that something is different. Okay, so maybe, because we looked at the means earlier, candy was 2 point something, cheese and fruit were 5 and 6. Maybe cheese and fruit aren't different, but they're different from candy. So it's, you might, in this particular example, they're all like different because it's made up data, but you might have a study where 2 groups are the same and 1 group is different from those 2. That's really common. You might have that one group is different from these other 2. And so the question isn't that they're all different from each other, it's something is different somewhere. So it's kind of funny we were talking about being detectives this morning, because ANOVA is actually kind of like a detective game. Did something happen? Okay, now what? That's the question. All right. So the next step, okay, I just wrote it out like this. So we'll want to calculate those example means, so we know what we're comparing, and then we'll calculate the summary table. Okay. So to get the means, it's a summary of the data set, which we've done, so let's do that. Means, chapter, we've actually already done this, but. So you can cut and paste this output in there. I'm really interested in the means. We're not going to use those at the moment, we're going to use them later, but that's what I'm most interested in. Right. And then the other thing we would do is actually run the ANOVA, okay, which I know we don't have time for. So we're going to stop there, and I'll let you ask any questions you have about tests or any of this stuff. This section is where you'll spend some time restructuring the data. So the biggest problem that we have is to make the ANOVA run, you can't be in this format. It has to be in a slightly different format. And then you will run it with Easy ANOVA. So if you're doing any of this work on your computer at home or in the lab, you'll need to install the Easy library. Okay. All right, so let's